Here's problem 24-9. Two infinitely uniform charged flat surfaces are mutually perpendicular. One of the sheets has a charge density of plus 60 picocoulombs per meter squared, and the other carries a charge density of minus 80 picocoulombs per meter squared. What is the magnitude of the electric field at any point not on either surface? Let's see if we can draw what's going on here. Let's set up one plane, our first plane, in the YZ plane. It's positively charged, and we're told that the sigma for that is, let's call it sigma 1, 60 picocoulombs per meter squared. Let's set up the other plane in the Z X direction. It's negatively charged, and the sigma for that, let's call it sigma 2, is a negative 80 picocoulombs per meter squared. As a result of the first sheet, positively charged, there will be an E field emanating away from it. So at some point, there will be some field, let's call it E1, emanating away from this on either side of that sheet. But we're going to look at some point, as we see in three-dimensional space, XYZ, as we've shown. With a negative sheet, there will be an electric field coming into it, into the negative charge. Let's call it E2. So these two fields will end up perpendicular to each other like that. If we can find the magnitude of these two fields, then we can add them together vectorially using the Pythagorean theorem and get the magnitude of the resultant field, which will be some kind of vector that looks like this. Alright, so let's do that. The magnitude of E1 is going to be sigma 1 over 2 epsilon naught. That's going to be 60 picocoulombs, 60 times 10 to the minus 12 over 2 times 8.85 times 10 to the minus 12. The 10 to the minus 12s will cancel out, and so we'll have 60 divided by 2 divided by 8.85, and that gives us 3.39 newtons per coulomb, and as I've drawn it, it'll be going to the right. Okay, the other field, E2, will be equal to sigma 2 over 2 epsilon naught, and that will be equal to, at least in magnitude, 80 picocoulombs, 80 times 10 to the minus 12, over 2 times 8.85 times 10 to the minus 12. And again, the 10 to the minus 12s will cancel out, so I'll have 80 divided by 2 divided by 8.85. That's 4.52 newtons per coulomb, and that field will be going down like that into the negative plane as I've drawn it. So we actually have these two fields. We have E1 equal to 3.39 going to the right, newtons per coulomb, and then we have E2 equal to 4.52 newtons per coulomb going down. They're perpendicular. We want the magnitude of this electric field, so we want the magnitude of that vector right there. In other words, if I wrote this as a vector, my total field would be equal to, as I'm drawing it, 3.39I minus 4.52 J newtons per coulomb, and I would just be finding the magnitude of that vector. So the magnitude of our electric field is going to be equal to 3.39 squared plus a negative 4.52 squared square root. If I square that, plus 3.39 squared square root I get 5.65 newtons per coulomb, and it's going down at an angle as I've drawn it like that. But the magnitude of the field is 5.65 newtons per coulomb, and it doesn't really matter where we are in this area here. Any of those points would have a magnitude of the field of 5.65 newtons per coulomb because the component fields are constant. And so we'll have the same field everywhere in that area, in that volume.